Okay, shall we start, or shall we wait?
No, I'm afraid we need to get started. People may still come dribbling in, but in order to stay,
True.
we need to start now.
Okay. Okay, good morning, everyone, and welcome to this exciting presentation on Power Functional Simulator. I'm Saif, Abrar, working with IBM on this Power Functional Simulation team, along with Brad, Tin Hang, Saqib, Vincent, Caleb, Ellen, Ravindra, and Nina. And together, as a team, we make this exciting technology that kickstarts your journey to the Power Open ISA. So today, I'm just going to give a brief introduction about this Power Functional Simulator, starting with the overview of the simulator, and then what are the different uses that it can be put into, and who are the different users of it, and then what are the interesting interfaces and the useful interfaces that the simulator provides, and a good amount of ecosystem around it. And then we'll open the floor for some discussions. To begin with, it's a full instruction set simulator. So the Power ISA that we have, so all the instructions in the ISA, they are simulated in the functional simulator. So all the instructions, and as and when the ISA gets updated, the simulator gets updated, and those instructions are available as part of this simulator. Also, it comes with a configurable system model. So there is a core model that simulates the instruction set, and then there is a small system around it that can be configured to tweak to the systems that people are interested in and they want to develop their software for. Interestingly, it has been used by the industry as well as by academics for all the different stages that the Power product is built for. For example, starting with the architecture exploration. So this can be used for that kind of a performance analysis. It can be used for the hardware verification when a new system is being built for, and the hardware has to be verified. So even before the hardware is available, the verification suite can be developed and it can be validated on this simulator. The OS bring up, for example, the Linux that you want to bring on your system, finally, it can be first brought up on this simulator and tested, and all the issues can be solved with that. The complete stack of the firmware that can be developed on this simulator and debugged and then finally ported onto the hardware. And if you have some applications that are built for other systems and you want to port to the Power systems, then that applications can be ported and then they can be tested on this simulator. And finally, the analysis and optimization. You want to optimize your application. So all those optimization cycles that can be done using this simulator. So for user friendliness, it is available to be executed on Linux and on x86. So there are all these different use cases in which the simulator can be used for. And yes, if you have some new ideas, you want to discuss some new engagements, we are open for that. So we have all these use cases that are already being catered to, and we are open to new ideas, new engagements going forward. So first of all, let us look how does it help the functional hardware verification. So anyone here working on the verification side or the validation of the hardware? So OK, let me just give you a brief about it. What do we need in a hardware verification is that the entire instructions that are there, that have to be verified, along with all the different the units within the cores that are there. So all those things are available in this simulator. So it's a golden reference implementation of the ISA. All the instructions that are there, that are available, as well as all the units within the core, the load store unit, the floating point unit, the vector unit, all those different kind of units that are within the core and that have to be verified by this verification suite, those complex interactions inside the core that can be done in this simulator. If you want to do some kind of memory or the translation effects, all these things are simulated in this simulator. So we call it as simply the simple mode of execution that runs about 1 million of instructions per cycle. So it's the lowest level of granularity and the simulation speed that is available for the verification suite. It is also supported by the advanced tool chain. So you can write your hardware verification suite, and then you can compile it or assemble it using the advanced tool chain, and then load on this simulator to make it work. So this is how it looks like. It works on x86 on top of Linux, and then this is the functional simulator. That is the goal inference model and the memory where the executable can be loaded and executed. The next interesting thing is the standalone applications. Those applications that you want to run directly on the hardware. So kind of a bare metal applications that doesn't need any OS support. For example, the scheduling or the translation by the OS. All these operating system features that are not required, the standalone applications, the user mode applications, they can be executed directly on this simulator. And for this, what is provided is a fast functional mode of simulation. So it has a very high speed of simulation. About more than 200 MIPS, 200 million instructions per second can be executed in this fast function mode that we call as the turbo mode, in which because now we are trying to execute the complete application, and the application developers, they want the highest simulation speed, and that is provided by this turbo mode. So what other control options are provided is that the user can switch between the simple mode and the turbo mode, so that while the application is being developed and you can run it in turbo mode, and when you want to debug the application, you can, within the simulator at that point of time, turn back to the simple mode and then debug instruction by instruction. You can run the simulation for a number of cycles, or you can single step through the simulator so that one instruction is executed at the time. So apart from the advanced tool chain, there are multiple debug options that are also available. We'll look more into it, what are the different debug options that are provided. So this is kind of, we have the fast functional mode, the turbo mode, the simple mode, and the standalone application executing on top of it. So just to give you an example, there is a small little demo about how does the simple mode and the turbo mode works together. Okay, this is better without it. So I can set the mode to turbo, and then I have an application of some random instructions that I can run, load on top of it through a tickle file. And since I've set the turbo mode to 0, so it is executing in simple mode, and as I told, it is pretty small, slow. It takes about 10 seconds to execute. And when I put the turbo mode as 1 and give the same command, then it gets executed within 2 seconds. So that is the kind of simulation speed that we get. So this was a very small application. For bigger applications, we see much more improvement in the simulation speed when we switch from simple to turbo mode. Okay, next about we can also do the complete Linux bring up on this simulator. And for this, a small system is also provided as part of the simulator. So only the core, the Linux cannot come upon. So we have models for a disk model, a network model, timer, UART, ROM. So a small system is built around the core so that the complete Linux can be brought on top of it. Also, the HPT and the Radix translation support is provided as part of the simulator. So the OS can be built for the Radix mode as well as for the HPT mode. And we also have available the Linux kernel, the ski boot, and a Debian disk image. So these are already provided to the users that they can download and start using on this available simulator. So just to give you an example, how does it looks like, a small demo of Linux bring up. So here I have my simulator, and I'm loading using this TCL file. So the simulation is running, and I'm just taking, it's a time-lapse video. So the Linux, the console has come up. So there are two consoles. One is the black console that is for the simulator, and this is the Linux console where the Linux is coming up on top of the simulator. And as we can see, it goes pretty fast, and it has booted. And I can execute some commands on Linux. So it looks pretty cool. Run some different commands, just for an example. On top of the Linux, the complete firmware stack can be developed using this simulator. So earlier we saw about the standalone applications that were without any OS support. And now this is the applications running on top of the Linux. So with all the features that the OS provides, like scheduling or translation or system calls, all these can be used by the application and run on it. For that, the complete simulation state can be observed to debug the application, to control this complete simulator can be controlled for execution. The register view, what are the register contents at a point of time, the memory dump, how does the memory is getting affected, all those things are can be controlled in this simulator. So we have the advanced toolchain provided. There are multiple debug options, and very powerful migration and code as advisors are also provided. So the migration, if you want to migrate from one system to the power system, so those kind of advisors are available. And then there are some code advisors that can give you some hint how to optimize your application. So in this way, complete OS or Linux-based applications, the complete firmware stack can be developed using this simulator. Moving on to some more interesting use cases, like we have performance analysis. Now, the complete architecture exploration and performance analysis, performance of the application as well as the performance of the system, both can be analyzed. And this is made possible by supporting the basic block vectors, the BBVs, which are the industry standard, to dump the information of the executing piece of software and then post-process it. Also, there are the M1 models that are provided. So this functional simulator just executes your set of instructions at a time. And then we have M1 models that we call, and these are also available publicly, on which, so these are much more fine-grained performance models, which can give you in-depth information about the architecture. So these are more at the micro-architecture level. So how does your application is, so we get the instruction trace using the functional simulator, and then post-process that instruction trace in the QTrace format on these M1 models. So you can get the cycle accuracy, or how the cycle by cycle instructions are progressing. What are the thread behavior, if it is on a single thread or a multi-thread, different pipeline stages that the instructions can go through, about the memory features, memory characterization, how the application is working as part of that. So all these things are, the analysis tools are provided. So from the functional simulator, you get the QTrace and the BBVs, which can be processed using these analysis tools. For example, there are the QTrace tools, which can dump in the QTrace format, as well as the QTrace reader is there, so that it can make the QTrace more human readable. Then there are some performance model, M1 core model, memory models. So pretty interesting set of features and tools available for very nice performance analysis. And what we have as part of the performance analysis, it can be visualized also. So these tools are also available. So once we have generated the instruction trace and the BBVs from the simulator and post-process this, then we have the complete visualization tools on top of them. So for example, you can get the CPI of your instruction, of your application, various statistics that are available. And then there is a viewer in which you can view the instructions, how they're progressing through the pipeline of a particular core. It's a Power 8 core or Power 9 core, or in future, the other cores that are coming up. So these kind of visualizations can be done by the supported tools as part of the functional simulator. So you see, it can cater to, starting from the hardware development suite to the OS bring up, to the functional, the firmware verification, to performance analysis, performance visualization. All these complete breadth of tasks can be done using this simulator. So as I mentioned earlier, many industry users are there, multiple academic users are there. So I'm just going to show some of the well-known users who have worked on it. For example, Google used this Power functional simulator to optimize the LLVM for the Power platforms. Rackspace, it developed and debugged the ski boot and the Linux using this the functional simulator. The Power core. So this is one core that was custom made based on the Power 8 core from IBM. So that was the performance analysis of that. This Power core was done using the tools that we discussed earlier. And with NVIDIA, we had this co-simulation of this functional simulator along with NVIDIA's own GPU simulator. So we have a broad class of industry use cases using this simulator. And if you are going to work on it and you have a pretty good use case, then next time you will have your name over here. OK, as I mentioned earlier, it's quite user-friendly. It gives you the complete simulator is abstracted as part of Tcl interface. So you get the power of Tcl and the simplicity of Tcl. So it's as simple as that. It comes with a default configuration. So for example, here I have a default configuration for P10. You can just duplicate it to your own configuration, and then you can update whatever features you want to update it for. And then you can instantiate your machine. You can load any application on top of it and just give it a run. It's as simple as that. So the power and simplicity. So you can have the Tcl commands. So user can interact with the simulator using the Tcl commands, and the simulator itself comes with its own commands. So you can mix and match. So there is as you saw earlier, there is the black display that was the controller or the CLI for the simulator, on which you can give the Tcl commands as well as what we call as the system sim. This is the official name for it. And then the Linux shell, you can execute the normal Linux commands on top of it. So just to, so you don't get overwhelmed by all of this, there's a good user guide that is available. And then there's a complete command reference manual that is available for users. So all that information is available over there. And then it comes with a very powerful graphical interface. As we all know, looking at a graphical picture is much more easier, and you can get all the information about the instructions, the registers, the threads, memory map, etc. To help you in developing your application, there's the debugger. The GDB can be attached, and the power is so we have this simulator, and top of it we have the machine that is being simulated, and the application is working on the simulated machine. And the GDB can control and debug the application that is running on the simulated machine. So you can normally attach GDB to the host application, but here we are attaching it to the application that is running on the simulated system. And then there are some runtime debug flags where you can actually look into how the processor is, or the system, the simulated system is working on. What are the registers that are getting executed? What are the instructions that are getting executed? What are the memory references, the translations? All these runtime debug flags are available for debug purpose. There's a very powerful feature that enables you to interact with the host. So this is the application running on top of the simulated system, the Linux. And then we have the host Linux. And then we have the Callthru by which the application and the Linux, host Linux, and the simulated, the Linux on the simulated system, they can communicate together. And then there is a disk support and the network support that is also provided as part of this simulator. So that we have a disk model, and then this is the disk on the host. Similarly, this is the network on the host, and the simulator can actually communicate to the disk on the host or the network on the host. So the block devices that are connected to the host, they can be configured, or they can be accessed from the simulator. Similarly, using this network, the simulator can connect to the physical network. To give you a demo of, I wanted to give you a good demo on neural networks. That is the most hottest thing. But the problem there is that these neural network applications, they take a long time and still longer on a simulator. So what I thought was to give you an example of a natural neural network. And the natural neural network is what we all have. It's not the artificial neural network, but the natural neural network is the fastest one. So I just made a demo application just to show you the Callthru. So it is the development stage that normally I develop my application, and then I compile it, see some errors, that again I go and debug my application, and this, we are trying to see that this is a C application. And when I compile and execute, so this is, I'm working on the host. Now I have done all my debug and development on the host, and now the application is ready to move on to the simulated system. So now we are going to see the power of Callthru. Now I can call through this, source this host application onto my simulated platform, and you can see that it is available here. Then I can put it to some other file and see that it is the same thing. And I can now giving all this compilation and execution in the simulated environment. So you see it is working as it was in the host. Now in the simulation, it works the same, and this is the GCC was on the, and I love this application so much, and I try to run it again and again. Okay, that was a small thing. So what we have currently available is the binary releases are available for Power 8 and Power 9. So you must be thinking about the next, what is there, and we have the Power 10 simulator coming up in second quarter next year. So we'll have the Power 8, Power 9, Power 10 simulators available to public. And then there is a good ecosystem around it. You can go to the OpenPOWER Foundation website. You will find a nice article about the introduction to it. Then, as I mentioned earlier, there is a user guide is available, the command reference manual, everything is available. And very interesting and powerful IDE, a complete software development kit comes for free download, where you get this functional simulator, you get the advanced tool chain that provides all the different compilation tools, etc. Then the performance analyzers, the viewers that we were discussing. So everything bundled together in this SDK. And for the users, we have a Customer Connect channel also. So if you have some advice, you have some feedback, you face some issues, you can connect back using this. So with this, we'll open up the floor for any questions and discussions. And I know that there are some already frequently asked questions. So I'll just answer them myself. And then, so it's currently available for execution on Linux on x86, as we discussed earlier. And it's only the binary releases that are available today. And it can be used for across the product development stages. And if you have your own custom simulation environment, there are features that I did not discuss yet, by which it can be used in your own simulation environment. So that is the power of this. So you can have the Power Simulator, and you can have your own custom simulation environment, and both of them co-simulating together. And if you have some new interesting ideas, you have some new engagements you want to work for your industry or for your academics, we are open for that. So you can catch me anytime. I'm available over here. And Also, you can feel free and you are welcome to contact me on my email, saif.abrar@in.ibm.com. And with this, we are in time for some questions. Yeah, thank you. Yep.
So this simulator runs on Linux on x86.
Exactly.
Have you ever considered porting it to Linux on Power?
Internally, we do it, but what I was mentioning was the binary that is available freely. That is only supported for Linux on x86, but within IBM, we run on Power also.
Would you consider making the binary available for Linux on Power? Because we want to increase the use of Power, and this might cause some people to go out and purchase a Power system, which is something.
Yeah, that's a nice feedback. I'll take it back to my team. Anton can also help in that.
Yeah, I was just going to say one thing. The interesting thing about simulating power is the optimizations that aren't available to running on top of x86. So the reality is, in a lot of cases, it runs faster, sometimes significantly faster than power box.
Very fast if it is on the Power
For
box.
example, the whole set of vector instructions.
Exactly.
You have to translate those to x86 vector instructions. On the power core, we basically just run them. And so in some cases, in the best cases, I'm seeing 100x speed ups on certain workloads when running on power.
So as we have more,
One good thing, and another good thing is Tim Pearson for Raptor.
exactly.
I think that's good feedback. I think we should go back.
Yeah, we'll take it back and we can discuss about it. That's a very good one. Yeah, we have time for a few more. Yes?
So regarding the simulated machines
Yes.
in the architecture, so I think you showed a picture that you can have multi-core.
Yes. Yeah,
You can also have SMT-enabled cores.
exactly.
Can you also simulate multi-socket systems?
You can have multi-socket systems. Theoretically, that is possible. The only thing is that the simulation speed degrades in that case.
Totally fine.
Yeah, but theoretically, yeah, that is possible, and that we do when we have internally, when we develop the firmware for the systems that IBM provides. So we run on the multi-socket systems. Yeah.
Oh no, running the simulator on multi-socket systems? Okay.
No. The simulated, the
System is
system is the simulated system is multi-socket.
So,
Yeah.
so with NUMA characteristics and cache currency protocol in place?
Yes, internally we have all those features available. Exactly.
So can you also configure different latencies and bandwidth interconnections between the sockets?
So these latencies part that comes as part of the performance analysis, that is done by the M1 models. And not in the, this is the functional simulator that gives you just the dump of the instructions. Because these M1 models, they cater to a specific core and a specific system. And then using these later post-processing steps, you can get all that information.
So would that be a different binary if you had a simulation of a multi-socket system? Would that mean that you had to have a different binary?
This is a simulator, and then we have another binaries that do the post-processing of the instructions. So you get the instruction trace using the functional simulator. That is in the QTrace format. That is a standard format. And this QTrace, you put as the input to the M1 models, and they give you all the different kind of statistics. And those are also freely available. Yeah?
Is there a reason why you didn't show performance delta between x86 and Power?
Pardon? I can come closer. No problem.
Is there a reason why you didn't show the performance improvement of OpenPOWER versus x86 of the simulation?
You mean the
So comparing, let's say, we were talking about the vector.
yes.
Is there a reason why you didn't highlight that in your analysis?
Okay, you mean the performance on the x86 versus the performance on Power?
Correct.
Okay, so here you mean that is a fast functional simulation mode on x86 and fast functional, the turbo mode on Power. So we have those figures But here, I'm just talking about the binary that is available freely, only on x86. So we are not going on the power domain.
Compare performance.
Yeah.
Trying to show the availability.
Yeah. Okay, do we have time for?
Yeah, actually, we do have,
Okay, good.
we're good until 15 more minutes, until 11:20.
Okay, yeah,
I want to ask about the toggle mode and the simple mode.
right.
But apart from you talked about the speed differences. Are there any other functionality differences?
Okay, so functionally, the software does not see any difference. The software that is executing, it doesn't know whether it is. Just think about a cache in hardware. So this, the application that is executing on the processor, it doesn't know whether the cache is there or not. So cache inherently speeds up the execution. Similarly, the turbo mode, so there are lots of techniques that go into making that fast functional model. For example, there is a just-in-time compilation. There's the translation, the instruction translation. There's the caching of the decoded instructions. So many practices that are put to make this turbo mode. But the application that is executing, it doesn't know whether it is executing in simple mode or turbo mode. So at the application level, it is transparent. At the user level, user can set whether he wants in the simple mode or turbo mode, and he can see the speed difference between the two. So application level, there is no difference, but the user who is using, he knows whether it is in turbo mode or the simple mode. And it's the technology is transparent. So you just have to set the turbo mode. That's all. The user doesn't have to do anything. In the tickle file, he just say, go into turbo mode, and the simulator goes into turbo mode. It's as simple as that for the user. Yeah.
So what exactly is turbo mode? I mean, what does it expose something that normally wouldn't? For example, I'm looking at, for example, security analysis. And you might have heard of spectrum meltdown. So
Yeah.
those exploits sidechain or products with cache system and other systems. So part of the microarchitecture, which we wouldn't actually have access to this normal mode. How would it be possible to use a simulator to or try to find or exploit some effects of the microarchitecture?
The simulator doesn't go into the microarchitecture details.
Okay.
So those kind of microarchitectural things, that is not possible in this simulator. It's only the instruction set simulator. You get read instruction, decode it, execute it. It's as simple as that.
One way to think about the two modes is interpreter versus JIT. So slow mode, you interpret your instructions, and turbo mode, you're actually JITting. You're creating code to run.
Yeah.
Is that about what is up race conditions or hazards in hardware? It's about problems with basically logic. This is what sections are.
Yeah, I understand. I guess the point is Saif was saying this is more architectural. So we're not modeling here a store queue that you can
Yeah.
or something like that. But you could probably build analysis into it to look for loads and stores and certain patterns, maybe look for a store board channel or something like that. So it would be possible.
Yeah. Okay, we have time for a few more, I think. If you've got some ideas, some feedback, where you want to use it, or how can we improve it, that's also good for us. Yes?
Perhaps another question about the simulated system architecture. So
Okay.
can I freely configure, like I want to have a theoretical P9 system,
Mm-hmm.
one socket and 100 cores.
Okay.
So is that possible? Is there a configuration file or so?
There is a configuration file. So the tickle file that I was mentioning, so I just showed an example of configuring the memory size and that. But you can configure how many cores are there, how many threads are there.
And so on.
Yes. So the tickle has, if you go through the command reference manual, you will get all these information over there. Yeah. Okay. We are still waiting for some more. or we can
All right, yeah.
invite the next speaker.
10 minutes before our next one, we can take a little break, and we'll start at 11:20.
Okay, thank you very much for your time and for your feedback. Thanks a lot.